All right, in this video, we are going to talk about the proof of Theorem 1.1.2, the Havel-Hakimi theorem. And I'm not going to go over the formal write-up of the proof, but you can see that in the book. Um, I really just want to talk about the ideas behind the proof and illustrate those ideas, and then you can take a look at how it's formalized. It's not as if I think that the formal proof is not important. It absolutely is. And excuse me, you should be taking a look at that, especially if you're going to graduate school in math, you're going to be proving a lot of theorems there. So you do need experience doing that. So, but you can see the proof of that. Okay, so first, remember the Havel-Hakimi theorem, how it goes, the statement of it. It says if we have these two sequences, sequence 1 is graphic if and only if sequence 2 is graphic, right? So it's really two proofs that we have to do. We have to show that if sequence 1 is graphic, then sequence 2 is graphic, and then turn around and prove if sequence 2 is graphic, then sequence 1 is graphic. Okay, and just don't forget the notation here, right? The notation for sequence 1 is S. That is the vertex with highest degree, and then these T sub 1 through T sub S, those are the vertices that are higher up in the sequence, right? And there are exactly as many of those as the degree of the vertex S, right? There's 1 through S labels here, and then the D sub I's, right, are the ones that come after that, right? All right. So let's take a look at just some of the ideas behind the proof. All right, so first we're going to start off with the easier direction, and that is if this sequence, T sub 1 minus 1 through T sub S minus 1, and then D sub 1 through D sub N is graphic, then that's sequence 2 in the statement of the theorem, then sequence 1 is graphic. So for instance, we have this sequence right here, 4, 3, 2, 2, 1, 0. And here is a realization of that graph, a graph whose degree sequence is exactly this sequence, right? And so if we say that T1 through 2TS are going to be these 4, all right, and then what we would do is we would add 1 to each of these and get 5, 4, 3, 3, and then have the S in that case would be 4, and we'd have to reorganize the sequence, right, or put it in non-increasing order. Okay, so here's what that would look like. All right, so this part of the proof is really pretty straightforward. What we are going to do, right, is we are going to add in a new vertex, and then we are going to take that new vertex and add an edge between that new vertex in every one of these vertices, okay? All right, so let's take a look at that. All right, so here's our graph again with the degree sequence. We are going to add a new vertex, and things that are added in, I'm just going to color in red so they're easier to see. So I'm going to add in a vertex G. All right, and then I am going to take and add an edge between G and the vertices, these 4 vertices right here, right, the T sub I's that are in there. Okay, and so that would be D. D had degree 4. It would be B with degree 3, and then A and C with degree 2. So A, B, and C, and D. I'm going to connect G up, right, to A. So A had degree 2, but now it will have degree 3. So it's one of these in the sequence. Vertex B had degree 3. So I'm adding another edge. So its degree will now be one of these, 4. Vertex C had degree 2. Right? So I'm adding an extra edge. So it'll be one of these 3s. And then vertex D had degree 4. So I'm adding another edge to it. It will be degree 5. And then G will be degree 4, right? Because it was a new vertex I added in, and then I connected it to these 4 vertices here. Okay. So that is really all that it takes for the new for the proof of that direction. Just add in a new vertex, and then connect it up with edges to all of your t sub i's. All right? Okay. So next up, let's talk about the more difficult direction, and that is if sequence 1 is graphic, then sequence 2 is graphic, right? So sequence 1, we had some vertex with degree s, and then we had the t sub i's, and then the d sub i's, right, in there. So remember, you have as many t sub i's as whatever the number is in the first spot in the sequence, okay? All right, and then what we need to show is that this sequence is graphic. So starting with a graph with this degree sequence, what do? And it's kind of the reverse, as you might imagine, right? The reverse of the first part. In the first part, we added in a vertex and then connected it up. And this time, what we want to do is take away a vertex, right? And then delete some edges. So there are a couple of cases overall that we need to consider for this direction. And the easiest case is when your vertex S, that corresponds to S here, is adjacent, right, to all of these t sub i's. So in other words, you have a vertex from S to T1, a vertex from S to T2, a vertex from S to T sub S, and so on and so forth. All right. And in that case, all you have to do is delete the vertex S and then delete those edges that are going to the t sub i's. It's that easy. All right, so here is an example. So here I have this graph, starting with this graph up here. You can see the S is 4, so that corresponds to this vertex A. A is the only vertex of degree 4 in this graph. And then the t sub i's, right, I'll have 4 of them, the same as this number, right? And so they are all 2's. And so it's B, C, D, and E. And you can see that A is adjacent to each of B, C, D, and E, right? So this is definitely the easy case. All right, and so what you would do is just get rid of A and get rid of all these edges right here. And you can see that's exactly the graph, the degree sequence that we would have by doing the Havel-Hakimi operation there, algorithm. I would get rid of the 4, so that vertex would be gone, and get rid of these edges, right? That would decrease these all to 1. So I'd have 4 1s, and then I'd have the d sub i's that are there as well. All right, so that is the easy case. If the vertex with degree S is connected to all of your t sub i's, then you can just get rid of the vertex that corresponds to degree S and get rid of all the edges, and then you're good. All right, so next up is the next case, and that basically is where it is not the case that your vertex S is adjacent, right, to all of your t sub i's. So in this particular example, right, in this particular graph that we're going to go through, and the S is 3, right, and that corresponds how I've got it to the vertex A here. All right, and now you may say, well, you don't have to do it that way. You could make this the vertex, right, that corresponds to the 3, and you absolutely could do that. But either way, you're going to have the same issues with this. All right, so the problem is, right, is that B, C, and D, all of those, right, those are my t sub i's in this case, and these are all my d sub i's. Then B, C, and D, none of those are adjacent to A. Okay, so that is a problem. Okay, so looking at the situation here, right, what I want to do is look at the overall, what I want to do, or what we're going to do in this part of the proof, is we are going to start making changes to this graph. We're going to start pulling out edges and putting edges back in. And that is going to give us, each time we do that, potentially, we're going to get a different graph than this one. The thing in that you might say, well, how does that prove anything? But the thing is each time we change the graph, we will see that the degree sequence is going to stay exactly the same, and that's important. Okay, so we'll be making changes to the graph, but the other thing to note is that the degree sequence is going to stay exactly the same. Okay, so and then in the end, each time we change the graph, our goal is going to be to get A to be adjacent to all of the t sub i's. And so you'll notice that each step we take, A will become adjacent to more of the t sub i's. So you can see here it's adjacent to none of the t sub i's. So each step we do, we're gonna change that. All right. Okay. So vertex A, right, is adjacent to some of the d sub i's over here. Okay. So it has to be, right, because it has the highest degree. Okay, and so looking at these d sub i's, right, all of these d sub i's, they have to have less edges, right, or less degree, smaller degree, are equal to than B, C, and D. That's the first thing to note, right, because the t sub i's are up here, right, these d sub i's are all going to have degrees less than or equal to the t sub i's, all right? So case one in this situation is where one of the neighbors of A, one of the vertices adjacent to A, has the same degree as one of the t sub i's here. So we can see that that G, one of the vertices adjacent to A, has the same degree, right, as D and C right here. And so if that's the case, we really don't need to do much of anything at all. All we've got to do is just switch one of these. We can say we're going to switch D and G is what we do here. All right, so that's it. So that's a pretty easy change to make. You can see that doesn't even really change the graph. You might say you could change the labels if you wanted to as well, right, and that would be fine. So here we didn't even really change the graph, and you can see that the degree sequence is unchanged because G and C had exactly the same degree, right? We didn't really change anything, and now, right? So now since G is one of the t sub i's, right? We have that A is adjacent to one of the t sub i's. So that's one more than we had before. All right, so we can play that game if we want to. And so then the other situation, right, is now that we still need A to be adjacent to B and D. Okay, and so we'll do that same thing. So next up, we're going to work on making A adjacent to B by changing the graph. But again, we want to keep the degree sequence exactly the same. All right, so A is adjacent to some D sub i's. And how do we know that? Well, it's the first in the sequence, so it has to be adjacent, right, to some other. It's the biggest degree of biggest vertex, right, in our vertex of biggest degree, right, in the graph. So it's adjacent to some of the D sub i's. So pick one of those out, right? So A is adjacent to E. And the important thing is that that since B now has bigger degree than E, right? B has degree 3 and E has degree 1, right? And so no matter what vertex we picked adjacent to A, right, if it's a D sub I, it has to have less degree than the degree of B. So what that means is that there is some vertex that's adjacent to B that is not adjacent to E. okay? And so in this case, we're going to pick that to be I. So that's really important, all right? The fact that there's some vertex over here adjacent to B that's not adjacent to E, which is adjacent to A. All right, and so what we're going to do then to make the switch or make the change right here, excuse me, is I'm going to delete the edge that goes from A, that's with the degree S as stated in the theorem, and this is a D sub I. I'm going to remove this edge, and I'm going to remove this edge. All right, so that means that the degree of E and A will drop, and the degree of B and I will drop. Then I'm also going to add in now an edge that goes from A to B, and an edge that goes from E to I, and that will, since those degrees dropped, adding two other edges back in will increase those by 1. All right, so take a look at what it looks like. All right, so I remove this edge from A to E, and I remove this edge from B to I. So we have a different graph now. I've added in these red ones, right? The red one goes from A to B. The edge E to I is added in here. So take a look at the degrees now and how they've changed, right? Remember, we had this edge in here before, so the degree of A was 3. That's gone now, but I added this edge in. So the degree of A is now unchanged. B had an edge between B and I, right? So it was degree 3 with the others. I took that one out, but then I added this one back in. So the degree of B is unchanged. And now notice A and B is one of the T sub i's, they are adjacent to each other. E was degree 1 before, okay? And so I took the edge out from the graph that we had before in the previous step, but then I added this one back in. So E is still degree 1. Same thing with I, right? I was degree 1 because it had an edge from B to I. I removed that, but now I have this edge back in. So this is a totally different graph than I had before, but it has exactly the same degree sequence, okay? So that is important. The degree sequence is unchanged, right? All that was possible was because of the fact that B in this graph had a higher degree than E, right? We knew that had to happen because this was one of the D sub i's, right? And this was a T sub I. So its degree, this had to come before E in the sequence, right? So there was an extra vertex floating around, right? That was adjacent to B, but not adjacent to this neighbor of A, right? And that allowed us to make the switch. All right, so now we have two of the T sub i's. We have B and we have G, right, adjacent to each other. So we're going to do, so now we're one step closer. The last one that we have to fix is this one D right here, okay? All right, we know that A is adjacent to some D sub I, all right? In that case, it's F, all right? And here is our last T sub I that we have to connect up to A. All right, so what that means is, again, since D is a T sub I and F is a D sub I, right, we know that the degree of D is bigger than the degree of F. So that means that there is some neighbor that is vertex adjacent to D that's not also adjacent to F. All right, and so we're going to do that same thing. We are going to switch, right? We're going to remove this edge from A to F, this from D to N. I believe that's the one I picked, yes. So we're going to remove these two, and then we're going to add two back in. One going from A to D, that will connect A up to the last T sub I, and then we will add an edge from F to N, right? So that, or between F and N, so that will keep the degrees the same, right? So it looks like this. So again, we get a totally different graph than we had in the previous step, right? But the degree sequence is exactly the same, exactly. right? Just verify that. A was degree 3 before. I removed this edge, but I added this one back in. D was degree 2. I removed this edge, but I added this one back in, the one between A and D. So its degree stayed the same. F was degree 1, and I removed this edge between A and F, but then I added this one between F and N back in. So the degree of F stayed the same. This one, N was degree 1. I removed the edge between D and N, but then I added this one between F and N back in, so it stayed degree 1. All right, so all of the degree sequence is exactly the same, completely unchanged, right? And now you can see, right, that now we have the effect that A is adjacent to B, G, and D, all of the T sub i's. All right, so each time we do one of those two operations, right, depending on the situation, and each time we get a different graph, right, the degree sequence, though, is exactly the same on every step, right? And since the graph is finite, this process has to end, right? We're only talking about finite graphs here, so we can't keep doing that repeatedly forever and ever, right? We'll eventually, each step, if we add a new, we get S, the S vertex, which is A in this case, adjacent to all of the T sub i's, then eventually we're going to, since we get one more in each step, eventually that process is going to end. So what we have is now we're back to the easy case where the vertex corresponding to degree S is adjacent to all of the T sub i's. And so the very last step is to just pop A out and all of the edges associated with it. So that's going to look like this. So A is gone. I removed the vertex that went from A to B, A to D, and A to G. Okay, so you can see these are all going to drop by 1. These are all going to remain exactly the same. And then, of course, I'd have to reorder this and put this 2 up in front. Okay. All right, so that is the idea between about the proof of the theorem. Okay. All right, and so you can see the formal proof of it in the textbook. I want to talk a little bit about the homework. Let's see the next set of problems to take a look at. So let me pull that up. And make sure. Okay, so the homework 2, right, is just running for the most part, it is just running through the Havel-Hakimi algorithm. Although some of these you might be able to do using the criteria that we talked about earlier. So basically all you want to do is to, for these first 5 problems, is determine if the sequence is graphic, right? If you use one of the criteria, just state, which one that you're using. You would say it's not graphic because, whatever the reason is. It has, it's too short or whatever, okay? So those 4 criteria that we talked about. If it is, if none of those criteria apply, then use the Havel-Hakimi theorem. I want to see the steps as you work through. You need to show me, just like I did in the video, the degrees, how the Havel-Hakimi work through that until you get down to the last thing, and then sketch the graph, of the last sequence to show that it's graphic. Then these last 3 right here, it says sketch a graph with the given degree sequence. Those, I want you to use the Havel-Hakimi theorem an algorithm to reduce it down and then work back through that in reverse, just like I showed you. So I want to see the steps of how you construct that, starting with the end result of the Havel-Hakimi algorithm and then working back through up until you get a graph with this degree sequence. So I want to see the steps on these. Okay, and that's it on this one.